Hi guys, today we're going to be going over our measuring volume lab, and this is a really good lab. We completed it today here in the classroom, and I'm just going to go over the top part of your sheet with you, and then we're going to talk a little bit about the bottom, and since you're not here, I'll go ahead and do some measurements for you, and then hopefully you can use that to complete the second part of the lab, which is the density lab. Okay, so for the first part at the top of your sheet, you need to remember we've already done a length lab. And when we measure length, we're using, of course, one dimension. And we talked a little bit about area, which is a length times a width. So that's two dimensions. And what we're doing today is volume. So volume is a length times a width times a height. And that gives us a volume. The volume is combining several different fundamental units. Okay? We're multiplying three different lengths, which are all fundamental units, and that makes this a derived unit. Density is also a derived unit because it's mass divided by volume. So it's two fundamental units, but when you combine them, they become derived. The metric volume unit is the liter. Okay? We're not talking about puppy dogs. It's not a liter, it's a liter. So 1T. It has about the same volume as a quart. And another name for it is a decimeter cubed. So, in a liter, there are 1,000 centimeters cubed. So, if you remember from our length lab, this is a centimeter, right? It's pretty small. If I took a centimeter long, a centimeter wide, and a centimeter tall, it would take 1,000 of those to equal 1 liter. Here we have blocks. And these are very representative. They're actually about 1 cc each, 1 cubic centimeter each. So if I look at these blocks, I've got 10 across, I've got 10 back, and I'm 10 down. So there's 1,000 of them here, so this is approximately 1 liter. Now, two other ways to think about this. If 1 liter equals 1,000 centimeters cubed, well, remember when we talked about prefixes. Deci means 1/10, centi means 1/100th, and milli meant 1/1000th. So, if 1 liter equals 1,000 centimeters cubed, if I took away that 1,000, then a centimeter cubed would be equal to 1 milliliter. Okay, 1/1000th of a liter. And we'll use milliliters a lot in the chemistry lab. We'll refer to things as get 50 mLs, stuff like that. Now, if you work in the healthcare setting, a lot of times instead of calling them milliliters, they'll say cc's. So if you watch any medical shows, I know you've heard them say, give me 100 cc's of something stat. And cc's are simply referring to cubic centimeters. Okay, so these things are all interchangeable. Centimeter cubed, milliliters, or cc's. They're all the same thing. Now, let's move on. If we're working in really small units, okay, we've covered deci, which is 1/10, centi, which is 1/100th, milli, which is 1/1000th. We're going to get even smaller. And the way we get smaller is with a unit called the microliter. The microliter is actually written with this thing called a mu. It's kind of a weird looking M shape, but its tail hangs down a little bit. But it is 1/1,000,000th of a liter. So it takes 1,000,000 microliters to equal 1 liter. The dimensions of a microliter are 1 millimeter times 1 millimeter times 1 millimeter. And if we look at this, if there's 1,000 milliliters equals a liter, and it takes 1,000,000 microliters to equal a liter, then it's 1,000 microliters to equal 1 milliliter. That's a little confusing even for me. That's a lot to take in. But just so you have an opportunity to see it, and hopefully you'll gain a little better understanding of that. But the last one, there are 1,000 microliters in a centimeter cubed. Now, as far as measuring, if we're measuring a regularly shaped object, probably the easiest way to get the volume of it is to simply take a ruler and go length times width times height. If we're measuring a small, irregularly shaped item, the easiest way to do that is with water displacement. So we're going to take it, we're going to put it in a graduated cylinder, and we're going to see how much the water increases. A couple things: you have to make sure there's enough water in it so that it covers the object, but it doesn't overflow out. And it's a lot more accurate to use a graduated cylinder than it is a beaker. Okay, graduated cylinders force the water more up, they have a smaller surface area, so you get better delineation. Okay, whereas a beaker has a much bigger surface area and they're not nearly as precise. For larger irregular objects, you guys have never done this before, but what we're going to do is we're going to use this overflow can, and we're going to fill it up with water. Okay, I always hold a finger over it, fill it up till it's slightly over this nozzle on the inside, and then you're going to sit there and you're going to let the water drain out into the sink until no more water is draining. Try not to move it after you do that, because if you do, you might splash some extra water out. Once you do that, you're going to put your item into the overflow can, but make sure you have a beaker there to catch the water that comes out. Then all you simply have to do is measure the amount of water that you have in here, and you've got your answer. Okay, that is the displacement. A couple pitfalls: sometimes people don't fill the water all the way up to where the nozzle is. Then when you put your item in, the first amount of displacement is actually going to just raise the water level before it comes out. So you're losing some volume. So you have to be very careful when you do that. The way we measure liquids, very easy. We're just going to put them in a graduated cylinder and measure them. Now when you measure in a graduated cylinder, you want to look at the fluid level, but there's usually what's called a meniscus. There's a curve. And that curve can either be, this is my nice drawing of graduated cylinders, that curve can either be up, or that curve can be down, depending on some of the properties of the liquid that you're using. If the curve is up, you want to measure to the top of it, the center. If the curve is down, you want to measure to the bottom of it, or again the center. I always just remember to measure to the center of my liquid. Okay? You want to make sure your eye's down at the water level and you're looking straight across. These that we're using are in milliliters, and you want to make sure you're estimating one spot just like we always do. With the gas, we're not going to do this in this lab, so I'm not going to talk a lot about it, but we will do it in the gas laws. But you use a pneumatic trough. It's a little trough full of water, and you turn a graduated cylinder upside down, and basically the gas bubbles up and it pushes the water down, and you can measure the displacement that way. But we'll cover that in the gas law lab. So the first thing we got is the wooden block. So I'm going to measure the wooden block real quick, and I measure 88.5 millimeters in length. Okay, this goes to millimeters, and so I'm estimating one spot. That's my 0.5. In width, I've got 73.5 millimeters, and in height, I've got 17.3 millimeters. Okay. Now, if I multiply those together, I've got 8.5 times 73.5 times 17.3 equals, I've got this huge number, but I can only have 3 sig figs, right? So that is going to go to 113,000 millimeters cubed. Okay, 113,000 millimeters cubed. My plastic cylinder that I'm going to measure, I'm going to use by the water displacement method. So I'm going to look at my graduated cylinder. I have to see what the volume of water is before. So the volume of water right now is 55.2 milliliters. So now I'm going to add my plastic rod. I make sure I tilt this sideways. I've had people take glass ones, drop it in there, and bust the bottom of the glass. So be very careful. Tilt it sideways. You also don't splash water out this way. Let it slide in, and I'm going to take my new measurement. And my new measurement here is 65.9 milliliters. So again, I do the math real quick. I take the volume that it went to, 65.9. I subtract the initial volume, 55.2. Now when I do this, I can only go as accurate as the measurements. So both of them went to the 10th spot. So now for my significant figures, I'm going to go to the 10th spot. So I got 10.7 milliliters. Okay, 10.7 milliliters. For my aluminum cylinder, I'm going to take another graduated cylinder here. I'm going to look at my initial volume of water, and I've got 59.1 milliliters. I wrote this down before if you can't tell. And then I'm going to add my aluminum cylinder. When I add my aluminum cylinder, good, it goes up to 79.2 milliliters. So again, I do the math real quick. And 79.2 minus 59.1. And I get 20.1 milliliters. Okay, that was the amount of water that was displaced by that object. And the last thing, I've got this big rock. It's a big irregularly shaped item. But I've got this big rock. So I'm not going to do this here. I don't have a sink, but I want to tell you what I do. I'm going to go ahead and fill my catch can up with water all the way slightly above the nozzle where it comes out. I'm going to set it over the edge of the sink and let it set until all the water, the excess water, drains out. Now I'm going to go ahead, put my beaker directly under it to catch any more water that comes out, and I'm going to place the item inside. Now, the excess water is going to come out, and then I'm simply going to measure my beaker. And my beaker ends up being exactly 42.0 milliliters. Okay, well hopefully you can use these calculations and complete the next step, which would be the density lab. And hopefully you've learned and followed along. Thank you very much.